everyone, and thanks for watching Edupedia World videos. This is the second video in the topic Bohr model, and in this video we learn more about the electronic configuration of different atoms. Now, in the previous video we only discussed hydrogen-like ions, and we were able to mathematically deduce from Coulomb's law and Bohr's quantization rule a lot of the results which actually have been verified experimentally. Now we'll go on to atoms with more than one electron, and because the mathematics is complicated, I'll just give you the results and we'll not derive them. So the first thing to do is to understand the naming of different quantum numbers. N, which we up till now had referred to as the energy state, is also called the principal quantum number. Our goal here is to understand the electronic configuration. I'm sure you've studied that in previous classes before, and it usually goes like 2, 8, 18 and so on. So 2 in the first shell, and then you have 8 in the next shell and 18 in the shell after that. So now we'll try to understand why this sort of stuff happens, why these numbers behave the way they do. So n is a principal quantum number. It is always greater than 0. It can be 1, 2, 3, 4, something like that. Then within every principal quantum number there is L, which is called the orbital angular momentum quantum number. And its value generally ranges from 0, 1, 2 all the way to n minus 1. So there are n possible values. That means if we are in the third energy state, then the principal quantum number is 3, and L can have values 0, 1 or 2. L can only take values starting from 0 and going up to n minus 1. Right? And within each L there is another quantum number, ML, which is called the magnetic quantum number. And for each L, the value of M ranges from minus L plus 1, minus 1, 0, 1, 2, L plus 1. So it ranges from minus L to L plus 1. Right. So there are a total of 2L plus 1 possible values. Sorry, this is not, it doesn't go to L plus 1, this just goes to L. From minus L to L, right, the one before that would be L minus 1. So there are 2L plus 1 possible values. Now there are some names for these as well. N is referred to as a shell or a major shell, and L is referred to as a subshell. Right. So let's look at what this means in detail. For every value of n, you will have n possible values of L. For each value of L within those values of n, you will have 2L plus 1 possible values of M. Right. So, and then there is the most important rule in quantum mechanics, which is called Pauli's exclusion principle. And I don't like telling you all these things without giving the explanation. However, the explanation comes from quantum mechanics, so it's not really in your course. But these quantum numbers are in your course, so you need to understand them properly. Right. So Pauli's exclusion principle basically states that no two entities can occupy the same state. Right. So you can only have one electron in one state. You cannot have more than one electron in one state. And every state is decided by the values of N, L and ML. Right. So every electron can have one possible value of N, L and ML. You cannot have two electrons with the same value of N, L and ML. Right. Now, so Pauli's exclusion principle is valid for particles which are called fermions. And the only particle you know of which are not fermions are photons. Other than that, electrons, protons, neutrons, they are all fermions, and they all obey Pauli's exclusion principle. Right. So let's look at what that tells us. So first of all, let's just start with a random shell. Let's start with n is equal to 3. N is equal to 3, by the way, is referred to as the M shell. N is equal to 1 is the K shell. N is equal to 2 is the L shell. And N is equal to 3 is called the M shell. And that's the way names goes. N, K, L, M and so on. So for N is equal to 3, L will have values of 0, 1 and 2. And the values of L, which I told you are called subshells, are labeled, and I don't know the reason for this. There's probably some weird historical reason, but these are labeled to as the S, P, D, and then there's an F shell. So L is equal to 0, S subshell, 1, P subshell, 2, D subshell, 3, F subshell. Right. So N is equal to 3, L is equal to 1 will be the M shell and the P subshell. Right. The names of shells go like K, L, M. The names of subshells go like S, P, D, F. After F, it's G, H. I think there are some missing, but other than that, it's in sequence. You only need to know these three. Now for 0, ML can only have the value of 0. For 1, ML can be -1, 0 and 1. And for 2, ML can be -2, -1, 0, 1, 2. Right. So let's count the total number of electrons that can occupy the N is equal to 3 shell. 1 electron here, 3 electrons here, 5 electrons here. So we have a total of 9 electrons in the M shell, or in N is equal to 3. Similarly, if we had N is equal to 2, you can verify it at home. If you have N is equal to 2, then D won't be there, it will be just these, and you'll have 4 electrons in L shell. And you can only have 1 electron in the K shell. Right. So the first energy state, N is equal to 1, you can only have 1 electron. For the second energy state, N is equal to 2, you can have two values of L, 0 and 1. The first value will give us 1 electron, the second value will give us 3 electrons. So you can have 4 electrons in N is equal to 2. N is equal to 3, you can have 9 electrons. Now, some of you might have noticed that this is actually half of the number we were hoping for, 2, 8 and 18. We know if you look at a periodic table that N is equal to 1 can have 2 electrons. N is equal to 2 can accommodate a total of 8 electrons. N is equal to 3 can accommodate a total of 18 electrons. So where does this factor of 2 come from? Well, that is because an electron state is not just decided by N, L and ML. There is also a fourth quantum number, MS, and that is called the spin quantum number. And it can only take two values, either plus half or minus half. So actually you could have two electrons with the same value of N, L and ML, and still Pauli's exclusion principle would not be violated. Pauli's exclusion principle states there cannot be more than one electron in any quantum state, but it doesn't tell us what a quantum state is. For electrons, quantum state is comprising of these four numbers. So you could have two electrons with the same N, L and ML as long as they both have different values of MS. And now let's look at that in a generic form as opposed to for a specific shell. For the nth shell, you can have n values of L. For each and every one of those values of L, you can have 2L plus 1 values of M. And for each and every one of those values of M, this is ML, you can have two values of MS. Right? So the two electrons in N is equal to 1 state will have N will be 1, L will be obviously 0, this will be 0, this is half and minus half. These are the two electrons in N is equal to 1. What happens when N is equal to 2? L can have a value 0 and 1. For 0, ML will be 0, and for 1, ML will be minus 1, 0, 1. For this 0, MS can be half or minus half. For this minus 1, it can be half or minus half. For 0, it can be half, minus half, and for 1. So every n, l and ml, every one of these three quantum numbers, every set of these three quantum numbers can accommodate 2 electrons, one with the positive spin, or sometimes we refer to as the up spin, and the other with the negative spin, or sometimes we would refer to it as the downward spin. Now there's a little bit of math which I'm not going to do. Some of you who are interested in professional mathematics can actually try it. If you add these numbers, 2l plus 1 values for each L and n possible values of L, then what it comes down to is there are a total of 2n square electrons in each shell. There would be a total of n square combinations of n, l and ml, as long as you follow the rules that L is always smaller than n and m is always between ml is always between minus l and l. There are n square values. Each and every one of those can have 2 electrons, one in the up state and one in the down state. So there are 2n square electrons in each shell. So n is equal to 1 shell will have 2 electrons, n is equal to 2 shell will have 8 electrons, n is equal to 3 shell will have 18 electrons, n is equal to 4 shell will have 32 electrons. And this is in complete agreement with the experimental results we find. Our periodic table clearly suggests to us that the first shell has 2 electrons, hydrogen, helium. The second one has 8, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. And then you have the third row which has 18. Of course there are some exceptions which you learn in chemistry, such as sometimes the D shell fills before the P shell of the next subshell. But right now we will not focus on all these. So the things you need to remember for this is every n can have n possible values of L ranging from 0 to n minus 1. Each and every one of those L will have 2L plus 1 possible values of ML, and each and every one of those values of ML will have 2 possible values of MS. And these in total, assuming that no 2 electrons can have the same values of N, L, ML and MS, tells us that there can be 2n square electrons in each shell. Now, for the hydrogen-like ions we studied, the energy only depended on the principal quantum number. It was 13.6 times n square by z. But when you have more than one electron, the energy actually depends on both n and l. For a particular value of n, different values of l have different energies, and typically they go from lowest to highest. So L is equal to 0 would be filled first, and then L is equal to 1 would be filled. And these things give rise to electronic configurations such as 1s2, 2s2, 2p4. This would say that there are 2 electrons in n is equal to 1, which is what it can handle. There are 2 electrons in n is equal to 2, L is equal to 0, and it can only handle 2. And there are 4 electrons in n is equal to 2, L is equal to 1, whereas it can handle a total of 6. You generally won't have a configuration like 1s2, 2s1, 2p5. Because then this electron would actually fall down to this state, pairing this electron and lowering its energy. So energy is filled from lowest to highest. And you can look at your periodic table, and as you go higher in atomic number, you'll see various exceptions, so don't go too far. Z is equal to 40. You can actually see that there's a lot of agreement within the electronic configurations, what they're supposed to be and what they actually are. Right? 2n square electrons in each shell, because there are n square possible values of n, l and ml, and the spin can be positive or negative. This completes Bohr model. Thank you.